Vamos lá, vou falar sobre expansão do universo.
Once you're on a big enough scale, which means in practice more than about 100 megaparsecs or so. And the second principle is that everything is moving away from everything else. And the further apart two things are, the faster they're moving apart. Now this gives us a rather strange universe, Brian, a universe where everything is moving away, and no matter where you are, 10 billion light years away, you'd see the same sort of thing. Galaxies out to as far as you can see in endless procession, all moving away from you. Right.
Então, inicialmente ele está falando sobre a expansão do universo, né? Em relação a pequena partícula, né, que se expandiu e formou todos os elementos cósmicos que a gente conhece.
So, and we can think about the logical extension of that. You have this universe which is seemingly expanding. That means in the past it was different than it is in the future. Things are closer together in the past. And so that distance...
Sim, que todos juntos e que se expandiram, né? Como se fosse uma pequena partícula que se inflou e explodiu. E a partir dessa explosão surgiu o que nós conhecemos de elementos cósmicos, né?
Distance things are just dependent on time. So in some weird way, time and distance or space are sort of related to each other.
And that sounds a lot like relativity. In particular, the whole nature of space and time relies on Einstein's theory of general relativity. We dealt with special relativity in the Violet Universe course, but now we're going to talk about general relativity, which is, in some sense, the most fundamental theory of space and time and gravity. Now, Einstein came to this by pondering something that most people didn't think was an issue.
Right, so in 1907, he was thinking, as Einstein obviously did a lot, and he was thinking about the two types of mass that exist within physical theory of the time.
So, if you remember your there are, what is mass? Brian, how would you define mass?
Well, in my daily job, I think of mass as being the thing that gravity affects. So I have the force of M, and then M, big G, and then a distance between the masses. So there's a force.
Yeah, so that's one equation that uses mass. It's Newton's equation of gravity, force equals G m over r squared. And that's actually very similar to other force equations in physics, for example, the force between electric charges. Once again, you get 1 over r squared, and you get a constant that tells you how strongly a particular particle interacts with something, which in the case of electromagnetism is its charge, in the case of gravity is its mass. Yeah. So that's sort of saying that mass is a gravitational charge. It tells you how strongly something pulls and is pulled by gravity. That's all well and good, but there's another quite different place where mass comes in.
Okay, well, that is true. So, for example, if I was going to measure the force, I'd also have to worry about MA, F equals MA. That's Newton's one of his other big hits. So that one, that A doesn't necessarily have to be gravity. It could be something else. So
yeah, so I mean, imagine you're sitting by the harbour in Sydney and you have an oil tanker and you push it.
Yep.
You're applying a force, but it doesn't accelerate very much. But if you have a small speedboat, you push it, it'll move. So this is telling you how much something resists being pushed around. Some big bruiser doesn't like being pushed around very much. Some small wimpy thing gets pushed around very easily.
So yeah, so I can use this, for example, to figure out how I'm going to be accelerated by Earth's gravity. I take the force of gravity and the F equals ma, and I equate them, and I can say A is equal to this thing from Newton's law of gravity. And that's a very useful little way to figure out what gravity is going to do to me.
Yeah. So normally most people just said, okay, we've got one equation with mass, another equation with mass, learn them, repeat them in the exam, end of story. Where it took the genius of Einstein was to think, hold on a minute, you've got mass in F equals ma, and that's kind of like inertial mass. It's telling you how much inertia something has. And you have gravitational mass, which is telling you how strongly things gravitate. Why do they have anything to do with each other?
Right. And so not only do they seem to have something to do with each other, I think his big thought was he thought they must always have something to do with each other and they must always be equivalent. But that turns out to be kind of a complicated thing to think through, as Einstein found out.
I mean, for other forces like electromagnetism, it's not the case. You could have something with a very strong charge and not much mass, or something with very large mass and not much charge. So if you have an electric field, things will all accelerate at different rates. But if you have a gravitational field, the force is proportional to the mass and the inertia is proportional to the mass, so it cancels out, which is why, at least in a vacuum, when there's no air resistance, everything falls at the same rate. So that's telling us that these two things, which really have quite different concepts, one's about resisting motion and one's about a force, but they're proportional to each other. They are the same thing. Why?
So I don't think we know why even to this day, but it certainly, if you think that logical consistency, okay, here on Earth makes things work. But what happens if you want to throw in, you know, getting close to the speed of light? And then we know we have all those relativistic effects. Well, how do you make those things then always be the same?
Yeah, so it's a real puzzle. This is what Einstein's great thought was. Why these two things, which apparently have not much to do with each other, why are they related?